Hello everyone, welcome to Jigyasa's video tutorial series. Throughout the series, so far we have been exclusively dealing with the tool BWSim-5G simulator. However, there is yet another tool developed by Jigyasa called as 5G toolkit. So the distinguishing feature in 5G toolkit is it's actually a Python based library which can aid the user in designing and developing 3GPP compliant 5G-NR modules. Basically, using the APIs present in the 5G Toolkit library, something as complex and elaborate as channel models or physical channels, while something as elementary as CRC encoders, decoders, and symbol mappers can be designed. So, this experiment, modulation schemes in 5G-NR, is uniquely elementary in such a way that this video can be a gateway to the viewer's experience of 5G toolkit. So, what is modulation? The bare bones version of communication is the successful transfer of information bits, zeros and ones, from the transmitter to receiver. If you think about it, the bits by themselves, when transmitted over air, are extremely susceptible to noise, and therefore waveforms rather than bits are transmitted over air by the antenna. So these waveforms are otherwise called as symbol, and the process of mapping the bits to the symbol is called as modulation or symbol mapping. Everyone with the basic digital communication knowledge knows that the modulation is done by having a carrier wave, and the nature of the carrier wave decides a different kind of digital modulation technique that can be used. For example, in a PSK or phase shift keying, the phase of the carrier wave is varied, and in the quadrature amplitude modulation technique, the phase and the amplitude is varied. So what is a modulation order? Basically, the number of bits that are grouped together to form the symbol are called as modulation order. So what is the relationship modulation order holds with the performance? Think of it like this. When you have a higher modulation order, you basically group a larger number of bits into a symbol. So you have a higher data rate. However, at the same time, higher modulation orders are extremely susceptible to noise. Therefore, in unfavorable conditions, you can experience high bit error rates when you transmit using higher modulation order. Now that you have a bird's eye view on modulation scheme, we will move on to a slightly more specific area, that is modulation schemes in 5G-NR. The 5G-NR utilizes modulation techniques from pi by 2 BPSK, BPSK, QPSK and 16 QAM. So why exactly there is the plethora or quite a variety of modulation orders present? Think of it like this. 5G is designed to support enhanced mobile broadband, ultra low latency communication and massive machine type communication. So the requirements of each of these slices is different, and to support that requirement, the 5G-NR specification enables the transmission of bits with different modulation order based on the state of channel. Furthermore, if you take a look into the block diagram, there are several reference signals that are being transmitted and received, and one has to remember that each signal as defined by 3GPP has to undergo a particular modulation technique. So based on this, we can understand that 5G-NR supports a variety of modulation order. In this experiment, we are going to analyze what happens when we transmit at different modulation orders. This being a Python based library, any IDE that the viewer finds comfortable can be used for using the 5G toolkit. As I feel Jupyter Notebook is more easy for me to use, I will be using Jupyter Notebook. Initially, we import the subsidiary libraries of Python such as NumPy and Matplotlib, and a very functional knowledge of these libraries along with Python is more than sufficient to utilize Toolkit 5G to its fullest potential. And we import the necessary modules required for this experiment. So we are going to be using CRC encoder decoder, symbol mapper demapper, and we are going to basically transmit using over an AWGN channel, and the AWGN channel in Toolkit 5G can be implemented using the add noise API. So what is happening here is we have two stages in implementing a 5G-NR module using the Toolkit 5G. First, you have to create or instantiate the object, and then you have to call it. Here what we do is we instantiate the different objects that were imported earlier. We instantiate the encoder and decoder to be a 24-bit CRC encoder and decoder. Similarly, here we are going to perform a QPSK, and then the demapping method is kept as max log map, and then finally we have instantiated the AWGN channel. Now what is being done over here is we are first randomly creating bits using the numpy's random int function, and what a small information here is when the starting number here will be included and the ending number will not be included, therefore it's obvious that either the bits can have the value 0 or 1, and then we pass it through the CRC encoder. Here we symbol map it, and then with an SNR of 70 we are passing it through the AWGN channel, and here we demap it. After we decode the CRC, we will have the received bits and the CRC checks. And if you can take a look over here, these are the received bits and these are the CRC checks. One can use the browser to check. There is a numpy functionality called as np.all to check if all the values of an array are true, and in this case all the CRC checks come out to be true, showing that we have correctly mapped and demapped the bits. So is that sufficient? Going one step forward, we can calculate the bit error rate and block error rate as shown here, where we take absolute value and mean of the difference between the transmitted bit and received bit, while BLER is calculated from the CRC check. Finally, when we plot the constellation diagram, the blue points represent the transmitted symbol and the red points represent the received symbol. Further down, for a sound analysis, the minimal knowledge of Python based looping and data structures, what is done here is we are iteratively performing the same process for different modulation orders for different SNRs. So what do we gain out of it? We will be getting 3 different BER waterfall curves and therefore compare the results for different modulation order. Meanwhile, print statement is used to get a log of what exactly happens for each SNR modulation order combination. And when we plot it, this is what we get. Similar to what the explanation was, one can notice that QPSK has the best BER performance, while 64 QAM with the highest modulation order has the poorest BER performance. As said earlier, this is because when modulated at a higher modulation order, the symbol is highly susceptible to noise. So now you have an experience with Toolkit 5G and have a clear overview of what modulation orders are present in 5G-NR. That's it. We've reached the end of this video. In case you have any doubts regarding the implementation of this particular experiment in 5G Toolkit, you can contact the Jigyasa team. Thank you.